Lesson 10.5, Circles and Angles. An inscribed angle is an angle with its vertex on the circle and sides that contain chords of the circle. In the figure below, angle ACB is an inscribed angle and arc AB is its intercepted arc. Note that the angle and the arc are listed incorrectly in your unit guide, so you need to make that change. So let's talk about what this gives us. Our inscribed angle theorem says that the measure of an inscribed angle is half the measure of the intercepted arc. So when we look at the figure that they've given us, here's our angle, angle ACB. So it's this angle right here. The arc that it intercepts is arc AB. So we can do measure of angle ACB is equal to 1/2 the measure of arc AB. Sometimes it's more convenient to look at it the other way. If the angle is half of the arc, that means that the arc is twice the angle. So we could also say that the measure of arc AB is 2 times the measure of angle ACB. So let's investigate how we can use this. It says in using the diagram above, angle ACB is x minus 10 and the measure of arc AB is x plus 20. Stop the video for a minute, draw the figure, and label it. This is what you should be coming up with. Your labels have your angle at x minus 10 and your arc at x plus 20. So when we look at writing our equation, we can either think that the angle is half the arc, which gives us x minus 10 equal to 1/2 x plus 20, or if you prefer, you can think that the arc is 2 times the angle, which gives us x plus 20 equals 2 times x minus 10. Again, I want you to stop the video and solve both of these equations and show yourself that those do give you the same value. No matter which way you see this, you find out that x is 40. Always go back and double check your task. They wanted us to find the measure of angle ACB. So the measure of angle ACB is labeled x minus 10, so this is going to be 40 minus 10, or 30 degrees. So now let's investigate a corollary that follows directly from this. Corollary says that if 2 inscribed angles of a circle intercept the same arc, then the angles are congruent. This should be evident when you look at angles 1 and 2. Both of those intercept arc AB, so both of them would be half of the measure of AB. So angle 2 is also half of the measure of AB. So based on this, we can see that angle 1 has to be congruent to angle 2. Example 2 uses this information. It's important to note that F is not the center of the circle. You can't make that assumption. But they're giving us values, so I want you to stop the video for a minute and transfer the values to the circle. The hint they give us tells us to draw 2 additional segments to form a pair of similar triangles. If we connect the segment EA and the segment CB, what we can find is that angle AEB intersects arc AB and angle ACB intercepts the same arc. Based on that, I know that those 2 angles are congruent. You also have a pair of vertical angles right here. So by AA, we know that the 2 triangles are similar. Based on that, we can set up proportions of corresponding sides. So we can set up x over 1 equals 8 over 2x, and we can solve this to find the value of x. If 2x squared is 8, x squared would be 4, and x would have to be positive or negative 2, but we can't have negative length, so we're just going to choose the positive 2. So if I know that x is 2, they're wanting us to find EB, which means I need to know EF, and I need to know FB. Once I know those 2, I can add them together to find EB. Use your value for x and go find those 3 values. So you should be finding that the length of EB would be 6 units. All right, so let's move on to the next corollary. Corollary 2 says that an angle inscribed in a circle is a right angle if and only if its corresponding arc is a semicircle. So if I know this is a diameter, then I know it's a straight line, which means it's got 180 degrees. So this arc right here, I could say if I put the center here and we'll call it D, I could say that angle ADB is 180 degrees. That's a central angle, which makes arc AB 180 degrees. I can also look at that as being a semicircle, which is half of the 360 degrees. So angle ACB would intercept the arc that's 180 degrees. So now I know for a fact that this is 1/2 of the measure of arc AB, which is 1/2 of 180 degrees, which makes this 90 degrees. So let's look at this example. In the inscribed triangle, AC is 4 and CB is 6. Now keep in mind, things are not always to scale, so you have to go with the values that you're given. Our job is to find the radius. To do this, we do need to be told that AB is a diameter. So we're going to go with that, because now if AB is a diameter, I know that angle ACB is 90 degrees. So if this is a right angle, you can just use Pythagorean theorem. So I want you to stop the video now and go solve this. I want you to do this on your own. When we check your notes next time, this should be completed. Moving on to corollary 3, this tells us that a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. As a reminder, supplementary means that they add up to 180 degrees. So in this figure, what this is saying is angle 1, the measure of angle 1 plus the measure of angle 3 would be 180. This would also be true for the measure of angle 2 plus the measure of angle 4. That would also be 180 degrees. So let's use this fact to do example 4. Quadrilateral EFGH is inscribed in a circle. I want you to stop the video, draw a circle with an inscribed quadrilateral, try not to make it a rectangle, and label angles EF, G, and H. The vertices have to be in the order that they're listed. So when you get your figure labeled, that should look something like this. What you need to do is find the angles that are across from each other, because your opposite angles are supplementary. This gives us the equation that tells us x plus 20 plus 2x plus 10 has to equal 180. I want you to stop the video and solve this, and then use this information to find the measure of angle H. Hopefully when you solved it, you got x to be 50. You can find the measures of angles E, F, and G and subtract that from 360 to find H, but you could also recognize that H and F have to be supplementary. So if F is 45 degrees, angle F plus angle H has to be 180, making angle H 135 degrees. So let's talk about what happens when it's not a central angle, okay, or an inscribed. These angles aren't either one of those. Okay, here are my central angles on this first figure. If this is the center, that's a central angle, and we know that has the same measure as the arc. But this is not a central angle. Okay, so if I'm looking at this angle right here, it's not a central angle. It's also not an inscribed angle because the vertex is not on the circle. So let's look at our intersecting chord angle theorem. If two chords intersect in the interior of a circle shown below, then their angle of intersection is related to the arc in this way. The angle formed by our two chords, in this case we're talking about angle X, is half the sum of the intercepted arcs. Well, if I'm using these two chords, it intercepts arcs A and B. So angle X is 1/2 their sum. Let's use this information to do a couple examples. In our first example, we're asked to find arc BCD. If you notice, you've got this angle right here. So the 92-degree angle would be half of the sum of the two angles, or the two arcs that are intercepted. So that's going to be 34 plus, and I'm just going to call this arc X. So solving this, we get X to be 150 degrees, meaning that the measure of arc BCD is 150. We have a similar situation in example 6. But this time we're finding an angle. Angle PQR would be this angle right here. So I need to do half of these two arcs. Well, the problem is that we didn't get a label for arc PR, but we do have for the rest of the figure. So you're going to have to subtract what you've got from 360 to find the measure of arc PR. Then you can solve this problem fairly simply. I want you to stop the video and go through and do that. You should find that the measure of angle PQR is 45 degrees. So what if we move the vertex completely outside of the circle? We have a similar thing going on here, except instead of the sum, this is going to be the difference. In this situation, x would be 1/2 of b minus a, and you do need to be careful and make sure that the difference stays positive. So always subtract the larger one minus the smaller one. So let's look at example 7. Two secants intersect at a 30-degree angle outside the circle. The smaller angle is, or smaller arc is 50, and we want to find the larger one. So my angle is 1/2 the difference of your intercepted arcs. So when we go through and solve this, we find that x is 110 degrees. All right, so this takes us to our intercepted arc theorem. This is really the same thing. We're showing you two more cases, but rather than trying to learn 3 different formulas, really it's the same thing. Here, x would be 1/2 of b minus a. In this particular situation, that turns out that it's always b minus 180, but that's not necessary to memorize. Here, we'd have the same situation, 1/2 b minus a. So I want you to use that and go find this. Stop the video and go find the measure of angle JKL. You're going to have to go find the measure of arc JL, which I've done in green, and then transfer that over to your formula to find the measure of angle JKL. Our last theorem is the intersecting chord segment theorem. The intersecting chord segment theorem says that if two chords intersect in the interior of a circle, then the product of the segments of one chord is equal to the products of the segments of the other chord. We can prove this using similar triangles, but we're not going to take time on the video to do that. In this figure, what that translates to is that AC times CE is equal to BC times CD. So let's look at this last figure. Stop the video, and I want you to transfer the markings to the figure and set this up using our theorem. To get your labels, you have to think through the information you're given. We're given that AE is 11, so if I know CE is 8, that makes AC 3. DB is a little bit more difficult. If we know that DC is 10, if we let DC be x, that makes CB 10 minus x. Now we can set up the equation based on our theorem. Piece times piece equals piece times piece. So we're going to go through and solve this, and this is going to give us a quadratic. So we're going to need everything on one side equal to 0, and then we're going to go factor this. This factors nicely as x minus 4 times x minus 6, giving us values of 4 or 6. And that has to do with the piece that I allowed to be x. If CD is 4, then BC is 6. If CD is 6, then BC is 4. So when they want the value of x, the value of x is either 4 or 6. That's the end of our notes. So at this point, you should go do your Tier 1 and your knowledge check.